Okay, guys, welcome. Today we're going to talk about the independent repetition of an experiment and how it relates to probability. Okay, so we're going to suppose that we repeat an experiment n times. Now we can consider this as one large experiment with the possible outcomes just being a sequence of length n, right? And then of course each element of that sequence would be a particular element from your sample space for the original experiment, right? So you could say that the sample space is the set at S cross S n times, or S to the n, of these sequences, right? So now the number of outcomes, of course, would be k to the n, right? As long as your sample space S has k possible outcomes. Now, each sequence is equally likely, so this is, of course, a uniform probability space. And if we suppose that A1 through AN is some outcome of this big experiment, then the probability of getting that single sequence of events happening is 1 over k to the n, right? So I know this kind of seems weird and abstract without a concrete example, so that's what we're going to do now. So for example, if we toss two coins, the sample space for each coin is heads, tails, right? You have one or the other option. Now the sample space for both is coming from S cross S, or S squared, right? So it's all the different outcomes where you have first and second elements being from your sample space S. So I could have head, head, I could have tail, tail, I could have head, tail, or tail, head, right? So that's coming from S cross S, or S squared. And of course it's S squared because I'm tossing two coins. If I was tossing three coins, then it would be S to the third, four coins, S to the fourth, and so on. And of course, the probability of each one of these outcomes would be 1 over 2 squared, right? Which of course is just 1 over 4, right? So all this stuff is sort of relating to what we just said. Now, this models the idea where the outcome of each repeated experiment is what we call independent of the previous outcomes, right? And this just means that there's no measurable influence of one experiment on the other, right? So if you flip a coin and you get heads, it doesn't make a difference for flipping it again. You're still just as equally likely to get heads or tails, just as before. So we would say that that's independent. Now, formally, or more formally in regards to mathematically, we say that two events A and B are independent if the probability of their intersection is equal to the probability of each of their individual probabilities multiplied together, right? So we'll show that the example that I just sort of talked about, of course, is independent. So we're going to say that we toss two coins. Now, we'll let A be the event that the first coin is heads, and we'll let B be the event that the second coin is also heads. So we'll show that A and B are independent. So to show that they're independent, we want to show that the probability of A intersect B is the probability of A times the probability of B. Well, A intersect B is that we get heads, heads, right? Because it's the first coin is heads and the second coin is heads. So the probability of A intersect B, of course, is 1 over 4. And now each of these individual probabilities, probability of A, probability that the first coin is heads, is 1/2. And the probability that the second coin is heads is also 1/2, right? So of course we're going to see that if I were to do probability of A times probability of B, I'm going to get 1/2 times 1/2, which would be 1/4, which is the probability of A intersect B. So this shows A and B are independent. Okay, so that's the idea of independence. Okay, now as another example, we're going to toss a coin and roll a die. Okay, now we're going to let H be the event that we toss a head for the coin, and we're going to let K be the event that we roll a 5 or a 6. Okay, now we're going to show that both of these are independent. So now, of course, the probability of tossing a head and rolling a 5 or a 6, well, what do we need to do? Well, we need to take the 1/2 for getting ahead, and I also need a 5 or a 6, so that gives me 2 out of 6 possibilities. So that would give me a 1/6. Okay, and now, of course, if I want the probability of tossing a head, that's 1/2. And the probability of rolling a 5 or a 6 would be 2/6. And if I multiply these two together, it's the same calculation as before. We get 1/6. Right? So since both of these come out to be the same, H and K are independent. Okay, so that's the idea. Now, we're going to be given two events here, and of course the experiment is rolling a single die. We have the event E that we roll an even number, and we have the event T that it's divisible by 3. And we want to prove or disprove that these are independent. So of course, how do we do that? Well, we need to find the probability of E intersect T. So E intersect T looks like we're going to get just the event of rolling a 6. It's the only even number that's divisible by 3. So the probability of E intersect T is 1/6. Now the probability of E is a 3/6, or we can say is a 1/2. And the probability of T would of course be 2/6, or 1/3. So now if we multiply these probabilities together, we get 1/2 times 1/3, so that is 1/6. So again, since these two come out to be the same, E and T are independent. Okay, so that's one way that we can prove independence here. And of course, this is sort of weird because we're rolling a single die, right? And we have two sort of completely separate events. And if you roll an even number, it might seem that that would better your chances of giving a number that's divisible by 3, but it turns out that they're independent. Okay. So now in this, I think this is, yeah. So now in this last example, we're going to say that we're going to throw 2 dice, and we want to find the probability that the sum is 8. Okay. Now, this is, of course, is an interesting problem, right? Because how can we get an 8? So we'll let E be that the sum is 8. Well, how can that happen? Well, we can have a 2 and a 6. We could have a 3 and a 5. We could have a 4 and a 4. And then we could have a 5 and a 3, or a 6 and a 2. So it looks like our event E has 5 possibilities, right? So the size of E is 5. Now, if we roll 2 dice, how many possible outcomes are there, right? Well, if I roll 1 die, my possibilities are 1, 2, 3, 4, 5, and 6. Now, for my big experiment, if I'm throwing 2 die, that's R squared, right? And we won't list everything out, but we're going to have 36 possible outcomes, right? Because I have 6 for R, and then I'm crossing it with 6. So R squared will be 6 times 6, right? We showed before that A cross B has the same cardinality as A times B. So in this case, we're showing that R cross R, well, we're not showing it, we're just stating it, that R cross R is the same as R times R. Right, so our R squared is 6, so therefore the probability of rolling an even number would be the probability of E over R squared. So we're going to get a 5 over 36 would be the probability that they sum to 8. Okay, so that concludes this video on repeating an experiment where that experiment is independent, has outcomes that are independent of the other. All right, I hope you enjoyed, and I'll see you next time.